This title is called Variants of Logistic Regression. You know, just like the way we have a variant of COVID, I remember the other time during COVID, we got a situation where COVID was mutating to another. I think I heard about maybe the beta version or gamma version or whatever. So we also have that we also have variant of logistic regression. Okay, of course, before now, I actually walk you through logistical regression. Of course, we use logistic regression in a situation where we're trying to characterize relationship between a categorical response variable. Okay, but let me tell you this generally. Let me tell you this generally. What determines the type of regression to use is the nature of the response variable. I'm going to say that again. The nature of response variable actually determines the regression type. Okay, I just wanted to take note of that. When the nature of response variable is continuous, we were fitting linear regression, right? When the nature of the response variable is categorical, okay, we're using binary logistic regression. But you know what I want to do today? What of in a situation whereby the response variable is not continuous, it's not categorical, but it's a count, okay? I'm going to write that, a count. Take a look at this, a count, okay? Having a count, okay? Situation where your response variable is a count, okay? Then if you are seeking relationship between the response variable that is a count, okay, you're you're looking at the relation between that and some other variable, we're actually going to use a Poisson regression. Okay, please take notes. So I'm gonna give you some examples of this. Number one, let me tell you this. In statistical analysis, we use Poisson distribution to model rare events, event that occur in a blue moon, like talking about the number of persons killed by motor horse kicks in the Prussian army per year. Or you want to talk about the number of people in line in front of you at a grocery store. When you go to, don't forget the way customers arrive at a grocery store, they arrive randomly. Does that make sense? They arrive at random. Okay. And what is the probability that when you get to grocery store, there's going to be customers ahead of you? Okay. Now, in that situation, the response variable is neither continuous, non-categorical, but it is a count, like a number, something you can count. Does that make sense? And do you know that having people in front of you in a grocery store could depends on some certain predictor? Number one, maybe the store offer a discounted price. That is what normally happens during a Black Friday, where you're going to see a lot of, consumer behave in a way that when the price goes down, they always want to buy more. Does that make sense? Okay. Then that can also depend on whether there's a special event going on, like an holiday or a big sporting event and so on like that. Then I'm going to give you another example now. Okay. The number of awards earned by students at one high school. When you talk about the numbers of awards, that's a count. That cannot be continuous. That cannot be categorical. Okay. So the numbers of awards also fall under Poisson distribution. Okay. Now, predators of now the explanatory variables for that could actually be type of the program that the high school student enrolled into. It could be vocational, it could be general academic, and the score on their final exam. So what I'm trying to say is trying to introduce you to Poisson distribution, okay, and Poisson regression. What determine the regression type to use is the nature of the response variable. When the response variable is continuous, we normally try linear regression. When the response variable is categorical, we normally try logistic regression. When the response variable is a count, okay, then we're actually going to use there's something that we call a variance of logistic regression that we call Poisson regression model. Now, I want to tell you this. Both logistic and Poisson regression models, they are also types of linear model, but we call them a generalized linear model. Generalized. Okay, generalized. They are generalized linear model. Okay, generalized linear model. Okay, Poisson regression and the logistic regression are generalized linear models. But why logistic regression is used to model a categorical response, okay? But the Poisson regression, on the other hand, is used to model response that is a count, okay? Now, take a look at what I have here, okay? Take a look at this. For logistic regression, we talk about binary outcomes, right? Binary outcomes mean, two categories. But for Poisson regression, we talk about counts, okay? And let me also discuss a different regression type model. We use a different link function, okay? Now, please, I need you to pay attention. For linear regression, okay? The underlying distribution in linear regression is normality, normal. And the link function is identity. Identity means f of mu equal to mu. But in the case of logistic regression, you remember the other time, okay, we're no longer talking about normal, we're talking about binary or binomial. And what do we normally use as a link function? Logit. You know what I call logit? Logit means the log of odd ratio. That's what we mean by logit. Log of odd ratio. But what do we use in Poisson regression? Let me tell you this. Another name for Poisson regression is log linear model. Log linear model. That's another. You know why I call log linear model? Because Poisson regression use a log form. Okay, the link function is the log. Now I need you to identify the difference between different regression type as different link function. For linear regression, it is called identity function. For logistic regression, it is called logit. And for Poisson regression, it is called log. Logarithm, just log. You can say log of p. But in the case of the logistic, it is log of p divided by 1 minus p. What is p? Don't forget, p is the probability of success. Does that make sense? Okay, now we want to move right now. How do we write logistic? How do we write a Poisson regression model? And how do we interpret the model? Please, I need you to pay attention. Take a look at this. I'm going to write the log expected value of yij. Why do I have y subscript ij? Because we're always going to have, because we're talking about counts, we're going to have a contingency table, a table arranged in row and column, okay? Where I is actually going to represent the row, J is going to represent the column. So the log lambda ij, what is lambda ij? The lambda ij is going to be a predicted rate for a particular value in that cell. A cell is going to be occupying ith row and jth column in the contingency table. Okay, y lambda is just going to be the baseline rate. It's going to be a baseline rate, and there's also going to be a predicted rate for a particular outcome. Take a look at that. Okay, now there's something I needed to see. The full explanation. I just mentioned. What about alpha high? Okay, the alpha high is the rate ratio, that is effect of you being in row I compared to the baseline. What we're going to be doing here, we're going to be comparing effect of being in a group with a baseline. The baseline is going to act like a control. Okay, then what about the YJ? That would be the effect of being in a column J. Because when we are constructing a contingency table, we're actually going to have uh, two categorical variable cross-listed. And in each of the cell, what are you going to have in each of the cell? Number in each category. Don't forget, we use Poisson regression for a count. Okay. Now you're going to see that as time goes on. But you know what? I need you to pay attention now. I want to walk us through an example, and you're going to see why Poisson regression model is more appropriate here. What we want to predict is this. We want to identify some important variable that can explain the number of customers visiting a store from region. What determines customers visiting a store? Look at the number of customers, because you want to predict number of customers. Then you're actually going to use a Poisson regression, because Poisson has to do with a count. What determines the number of customers that will visit my store? You know what we did? We now identify some variables, maybe according to literature. Number one variable, number of housing units in the region. Does that make sense? Then the average household income. People actually going to visit a store and buy stuff depending on the average. They are depending on their income. Then the average household units age in the region. Then the distance to nearest competitor. At times, maybe I want to buy something. I'm just going to put it on the Google. I'm going to say something near me. Does that make sense? Near me. Look at that. Distance to the nearest competitor. Okay. Now, then average distance to the store in miles. Average distance to the store. When you take a look at distance to the nearest competitor, those stores that sell the same thing, I'm actually going to prefer to go to the one that is very close to me. Now, you know what I want to do here? Our observation is going to be we want to use a data set from 110 regions. Is there any question about this page before moving to the next page? Is there anybody here who doesn't understand what we want to figure out? Whether in person or online? We actually want to look at the effect of these variables on a response variable that is a count, which is the number of customers visiting store from region. Does that make sense? Okay. Now, you know what I want to do now? I need to first write the model out. I need to write a Poisson model out based on the number of predators that I have. If I want to write a Poisson regression model out, oh my God, look at that. That is the systematic part. Go ahead. That's a very good question. Somebody asked, is that a natural log or a regular log? Is a natural log. Okay, now, please, I need you to pay attention to this. We got two specifications of logistic regression, of a Poisson, let me say this. We got two ways of specifying Poisson regression model. Okay, and we have to specify the two. The one that you are seeing now is a systematic one that doesn't include error. Do you see that? Any question on this? If I want to write a multiple linear regression, instead of where you put I have log lambda high, I'm only going to have y for multiple linear regression, right? But for Poisson regression, that y will be automatically replaced by log lambda high. Then the probabilistic component is Poisson regression. It's Poisson. What we mean now is trying to say, okay, yi given xi follow Poisson distribution with parameter lambda I. Okay, and that lambda I, okay, you can see from the beginning we said log lambda I equal to that. That is the way to specify Poisson regression model for this particular question. But you know what? Can we have our data? Oh my God. This is the data that we collected for 110 region. Okay, it doesn't stop at 9. I'm just showing you the first 9. Does that make sense? Now you see customers. Do you see anything points? No, didn't see anything something points something or whatever. You didn't see 0, 1 like this is not categorized. This is a count data. Okay, whenever you want to predict a count data, this is a response variable that is a count. You want to look at that in relation to other predictors. You're actually going to use Poisson regression model. Okay, we got this data set. But let me tell you this. In order for us to justify to the world that linear regression is not going to work here, because the linear regression requires the distribution of the error and the distribution of the response variable to be normal. Do you know if you want to start, you can first look at the distributions of this guy, the probability distribution, to see whether it's not going to be normal. Take a look at this guy. Oh my God. You can do the histogram of a customer in our histogram of that. Is that normal? That's skewed, right? That's skewed to the right. Look at that. And that was why I said here, I said the customer count distribution is clearly not, normally distributed, as you can see, as given by the histogram. Take a look at that. Okay. And because of that, because there's going to be a violations of normality as of shown, then the linear regression is not going to work. Let me tell you this, you may fit a linear regression for this, and your p-value may tell you significant. Don't celebrate. You're using a wrong model. And that's how I used to tell you. The fact that somebody, when somebody commits an offense in the state of Minnesota, and this person is being tried, maybe the person ran to California, and a California court now tried this guy, even though the California court was able to establish the fact that he committed an offense, whatever decision they make in the state of California will be declared null and void. Because California does not have a territorial jurisdiction to answer the case. That suspect did not break a California law. That suspect broke Minnesota law. He should be tried using Minnesota law. So the fact that even if you fit a linear regression and you see significant p-value, don't celebrate. Okay. Now, how am I going to know log linear is going to work? Because this is skewed to the right. When something is skewed to the right, okay, skewness to the right, it's like moving to the right of the center. What do you want to do to bring it back to the center? You can compress by taking a log. A log of a big number will give you a small number, right? And that is why a Poisson regression is also called a log linear model. Log linear model. Oh my God. Initially, it was non-linear in nature. By the time I apply Poisson regression model, it becomes linear. That's what it means. Log linear. That it's another form of transformation. Does that make sense? It's another form of transformation. Okay. Now, how do we now fit this in R? How do we fit Poisson regression model in R? Okay. Take a look at this. Oh my God. Please pay attention. Please pay attention. Do you see GLM? Even when you are fitting logistic, it's also going to be GLM. But what is the difference between logistic code and a Poisson regression code? In the logistic code, under family, you're going to see family equal to binomial. But for Poisson, family equal Poisson. Do you see that here? Do you see that? Family equal Poisson. This is the different now. Okay. Now let's see the result. Oh my God. This is what I see that is different now. You're actually gonna see whether for logistic or for Poisson regression, they all belong to the same family. They are generalized linear model. That's why you see GLM. And generalized linear model, what you're going to see in the output is going to be Z value instead of a T. You know, in the linear regression, what do you normally see? T, right? But here you're going to see Z because Poisson regression is a variant of a logistic regression. It's another logistic regression in another form, just like the same way you have a variant of COVID. You know, in a COVID, I know initially we have a conventional COVID. There was a time the COVID was mutating, you know, where we have a different names, you know. That is why we call a Poisson regression a variant of a logistic regression. You know what? The same way that we actually try to look at the p-value, okay? When you take a look at the p-value, okay, housing has significant contribution. Look at the p-value, income, age, competitor, store, all the predator variables going by the p-value, they actually have a contribution, a significant contribution to the number of customers visiting a store from region. Now, this is how do we write a feeder model? Please, I need you to pay attention. This is very, very crucial. How do we write our feeder model? Take a look at it. This is a feeder model, right? That's a general one. And based on what I did right now, that's a feeder model. What do you think I'm using right now? You're going to come back here. Okay, we're going to come back to the estimate. You know, you're going to use the combination of that. Do you see that? Okay, now when you do that, can you see that? Is there any question here? But let me tell you this. Housing, it has a positive contribution. Can you see housing? The slope for that is positive, income negative, age negative, competitor positive, store negative. Take a look at that. But you know what? How do we do the interpretation with a Poisson regression model? Let's take a look at this guy now. I'm going to take it one by one. If I want to start my interpretation, I'm actually going to start from the intercept. That's what we always do, right? We're going to start our interpretation of whatever model from the intercept, right? Now, I need you to pay attention. The way we interpret intercept in the linear regression model is different from the way we interpret intercept in the logistic regression model. It's also going to be different. The way we're going to interpret it right now in the Poisson regression model, I need you to pay attention. Now, I'm going to take you to the interpretation now. Please, I need you to take note of this. What do we want to interpret now? We want to interpret intercept in the Poisson regression model 2.94. We are interpreting this as the baseline log expected count. Do you remember the way we call that in the logistic regression? We call them log odd estimates. In the logistic regression, we call those regression parameter log odd estimate. But right here now, how do we call beta naught in a Poisson regression? That is the baseline log expected count. If you don't put log, if you put expected count, you are saying a different thing. There's a difference between a baseline expected count and a baseline log expected count. The way the estimate is going to come from the regression output is going to be interpreted as log, as the baseline log expected count. And what do we mean? Okay, now we're trying to say, or we can say log rate. In the group, which all covariate, I'll say all of that is 0. Can I ask you this question? Does that really make sense? Okay, if you really want to know whether it makes sense, you know, somebody was going to say, oh, that is mathematically confusing. What do we mean by log? What do we mean by baseline log expected? Okay, let us remove log and say expected count, right? What are we going to do to remove log? We exponentiate in mathematics. If I want to remove log, what am I going to do? We exponentiate. That's an exponentiation. When something is log and I want to remove the log, I don't just remove the log because look at math. Let me write this. Exponential raised to power log. Exponential raised to power log A is A. And that was the reason why you asked a question the other time. Am I talking about just ordinary logarithm or the natural log? I'm talking about natural log. So exponential raised to power log, that very log is a natural log. Is another way to write exponential raised to power ln. Okay, that natural log A is equal to A. Does that make sense? Now, you know what I want to do now? I don't want to mention log anymore. I just want to mention, take a look at that. That will be the expected count at a baseline. When I say expected count, it means when there is no housing, no income, no age, no nothing, that will be the number of customers that will be visiting. But let us take a look at this. If all of that is zero, are we going to have any customer at all? And that is why it is not all the time that interpretation of intercept makes sense. And that was what I'm trying to say here. I said the baseline value does not quite make sense. But why do we need it? We need it. I said it may be helpful to set our covariate. That would be, because we need to start from a baseline. We need to start from somewhere. Okay, to set our covariate, but you know what is necessary? I said, but this is not a big deal if we don't care about the baseline, because our primary inference is about the increase with the respect to covariate. That's what we're interested in. We are only interested in when housing unit goes up. What will be the effect on the number of customers visiting store? When age increases, what will be the effect? That's what we're interested in. Does that make sense? Okay, any question about the interpretation of intercept right now? Okay, now I want to go into the interpretation of individual. You know what I want to do now? Actually, I want to first start with income, or let me see. Okay, I'm starting with beta 1. Okay, actually I want to start with housing. If you go back to the module, okay, can you see the module right now? You see the housing, you see that 0.00 something. Okay, now how do I interpret it the way it is? Okay, please, I need you to pay attention. I must mention log again. Okay, take a look at this. I said this guy, okay, that is the increase in the log expected count. Increase in the log expected count or log rate ratio comparing district whose number of housing unit differ by 1. Adjusting for other covariate. Don't forget, why do I need to mention adjusting for other covariate? Don't forget, I'm looking at the effect of housing in the presence of other covariate as well. And other covariate has to be adjusted. Do you see that interpretation of that guy? But you know what? If I want to remove the log again, I want to remove the log again. Okay, what am I going to do? Oh my God, I'm going to do exponentiation. Do you see why I'm doing exponentiation? Because I want to remove the log expected. I want to just talk about expected count for a unit increase in housing. When the number of housing in that region increased by 1, that's what I mean. Okay, now exponentiation of that. Now give me that. I got a new value. 1.000605 is a rate ratio comparing district whose mean housing unit differ by 1, adjusting for other covariates. But let me tell you this. Somebody may be saying that is too small. Like considering housing unit increased by 1. Why not considering increasing by 100? Does that make sense? What would be the effect of that 100? Now take a look at what I'm saying here. What am I doing? Before I exponentiate, I multiply beta 1 by 100. It means I'm not interested in the unit increase in anymore. I want to look at the effect of 100 unit increase. And that was, and I give that, said, that is the rate comparing district whose mean housing will be divided by 100. You can also do the one, maybe divide by 1,000. Does that make sense? And let me tell you this. How do we interpret this guy? You know the meaning of that, right? That's over. That is, if you want to understand the meaning, multiply it by 100. If you multiply it by 100, if 100 is the baseline, how many percent increase? That would be 6.2%. Do you see that? And that was why I said, keeping other factors constant, a 100 unit increase in housing unit will yield an expected 6.2% increase in customer count. Does that make sense to you now? Okay, now I can do the same thing for others. This is just talking about housing. I'm going to go to something more, another one. Okay, now what I'm trying to say here is to tell you that we use a Z statistic, the p-value, and of course we take a decision on that. Now let's go to the next one, beta 2. The beta 2 is the one that has to do with income. Okay, if you go back to the model, income was a negative. How do we interpret this guy? Interpreting directly from a Poisson regression output, don't forget, you're always going to put a log. Now look at what I said. To be increase in the log expected count, okay, or log rate ratio, comparing district whose mean income differ by $1, just $1. What comes from the table when you are interpreting the slope from the computer output or the arrow output? If you are interpreting that directly, is talking about a unit increase. If it is income, $1 increase. If it is housing, increase in one unit, one house increase. Okay, but you know what? If I don't want to talk about log anymore, okay, I'm also going to do the same. This is that exponentiation. We're going to be talking about the expected now. Okay, now that guy mean the relative rate comparing region whose mean income differ by $1, adjusting for other covariate, but $1 is too small. Can we go for 1,000 or 10,000? Let's take a look, because we're talking about region, comparing region to region. Take a look at this. Oh my God, what am I doing here? I want to look at the effects of, the $10,000 now. Region whose, the comparing region whose income is differ by $10,000. We want to look at the expected. So account. Now, when you do that, that gives you this. Okay. Now, I said this is a relative rate comparing region whose mean income differ by $10,000 adjusted for other covariates. I want us to interpret this. Look at this value here. It's less than 100, right? If you see that, it's not less than 100, 0.88. That's less than 100. Now, if you subtract that from 1 and multiply, that is 11% decrease. Okay, so which means for a 10,000 change in average income, we will predict an 11% decrease in the rate of customer visiting. That is not surprising. You know why it's not surprising? Because the slope for income was negative. Then you expect a decrease. Do you see according to the data? Do you see negative? Take a look at that. Let me tell you something. The income here is contributing negatively to the number of customers arriving. Some of you may be thinking opposite. At times, it is not the more income, the more customer going to visit the store. They could divert their money to something else. See, imagine I won a jackpot today of $1 million. There's possibility that I may not even buying from where I used to buy again. I may change my level. Is that going to be a different thinking behavior? Okay. Now take a look at that. That's what we mean. Now we also talk about confidence interval here too. But let me say this. If I want, I can find the confidence interval for each of the parameter in the, if you take a look at this guy, if I want to find a 95% confidence interval, of course, I can go back to the table. If I want to get confidence interval, I just need the estimate and the standard error. See, if I need this estimate and the standard error, even the z-test it is estimate divided by standard error. 2.94 that divided by 2.07 is giving 14.1. Even the z-test that we conduct, it is the estimate divided by standard error. If I want to do the confidence interval, why am I interested in doing the confidence interval? Because the value that we have here, give me 1 second. The value that we have here, they are point estimates. A point estimate when you have a single value could be wrong or right. And that's why we want, well, can we have a way, instead of having a single value for housing, can we have it in an interval? Can we have age also in an interval? Can we have income in an interval? Can we have the regression estimate here in an interval for Poisson regression as well? Of course, that can be done. And if I want to have it in an interval, I'm actually going to use the formula here. Do you see that? For instance, I want to do beta 2 for income. It's going to be beta 2 for 95% confidence. It's going to be beta 2 plus or minus 1.96 standard error of the beta 2. When I plug that in, but I need to pay attention. This guy here is the confidence interval for the log, expected log. But how can I have an interval for the expected if I want to remove the log? I just need to take the exponentiation of what I got here. I don't know whether that makes sense to you. Just take the exponentiation of lower bound and the upper bound. Then I'm already in the expected. Do you see that? And do you know, the other time I was talking about $10,000 difference between two regions. How can I also compute? The other time, take a look at this. When we consider only the point estimate, that gives us 0.889. 0.889 is a point estimate that could be wrong or right. How do we get an interval estimate for that? Don't forget, what you do to get a point estimate was exponentiating that guy. You know what I'm going to do right now? I'm just going to come here. Take a look at this. This is going to, do you see this guy? Right? Now, if I want to do the one for 10,000, I'm going to use the one I got here. Okay, before I take the exponentiation, you can see that this guy is do you see the lower bound here? Do you see the upper bound here? What are you doing? You multiply each by 10,000 before you take the exponentiation. That is to get the interval for that. It's actually going to make more sense when I speak in interval. It's going to make more sense to say, okay, it lies between 0.854 and 0.927 than to just say it is 0.889. 0.889 could be wrong or right, because a single value could be wrong or right. Okay. Now, do you know that if I want to interpret this guy now, okay, each of these less than 1, right? If you subtract each of them from 1 and you multiply by 100, then you'll be able to say the decrease is going to go from this to that. Does that make sense? it make more sense working with an interval than just focusing on a single value that could be wrong or right. We don't want a situation whereby we've committed a lot of resources to research only to be let down by using poor statistical tool. Okay, you see that now? You know, look at the new interpretation that I have for the confidence level. Now I'm going to say 95% confidence for the relative rates of customer visiting the store is that for a 10,000 increase in average income for the region. Because, you know, a mayor of a city or the government of a region, of a place, we need to consider what would be the effects of $10,000 increase, okay, in average income for this region on the numbers of customers that will be visiting. So maybe you don't forget those stores, those one in business, they're also paying tax, and they may be complaining to government that we don't see people patronizing us. What is going on? And government, and that's why at times government may introduce a palliative measure, like at times giving out free money to people. Go and spend. There's a lot of things going on. Okay, so they need statistical advice for them, a government that is not doing well. Maybe it's not paying attention to figures, or maybe it's not listening to people. If you really want to do well in governance, okay, you need to be statistically guided. Does that make sense? Now, take a look at the question now. Based on this model, I'm asking you this question now based on what we've done. If we are going to choose a location to build a new store, should we choose area with higher or lower income? Does it matter? You can answer that using, if you want to answer that based on this particular data, based on the contribution of income. Okay? Now I'm going to go to summary now of what I've just introduced today. So Poisson regression gives us a framework in which to build model for what? For count data only. Okay? And it is special case of a generalized linear model, and it is closely related to linear and logistic regression modeling. Don't forget, they got different link function. For linear regression, the link function is identity. For logistic, it's actually logit. For Poisson, it's log, lambda. Okay. Now, I said all of the same modeling technique we carry over from linear regression, what we've been doing, whether in linear regression, whether in logistic regression, whether in Poisson regression, we can also adjust for confounding. Adjust for confounding is when you incorporate more variables. For instance, I'm looking at the effect of housing, and I also put into consideration effect of keeping constant the effect of income and so on like that. That is controlling for confounding. Okay, then allow for effect modification by fitting interaction. We can, even whether you're working with logistic regression or linear regression or Poisson regression, we can also do variable selection in Poisson regression as well. Does that make sense? We do a lot of stuff that we did in linear regression, even in Poisson regression. Okay, now we can test significance of regression coefficient using Z statistic. I'm seeing some exam question here. In linear regression, if I want to test significance of regression coefficient, what do I use? T-test. But in a logistic regression and Poisson regression, it is Z-test. You can see the Z, right? Okay. And I said, since Poisson regression specify a model, we can conclude likelihood. Likelihood ratio test can also apply. Let me tell you this, the same way we did under linear regression, that we're comparing nested models. Nested models, right? When you compare simple model with complicated, we can do that also in logistic. We can also do that in Poisson regression. Okay, now, and don't forget, we need a new interpretation for regression coefficient. The way we interpret regression coefficient in linear regression is different from the way we do in logistic and the Poisson regression. Okay, don't forget, we normally talk about log. When you talk about Poisson regression, we talk about log. When you talk about logistic regression, we also talk about log. Okay, but in the logistic regression, when you are interpreting, when you talk about log, you make reference to the occurrence of the primary, to the probability of characteristics of interest. Okay, now here, we interpret the intercept as what the other time as a log rate for the baseline, or log expected count for the baseline. What am I going to do to remove the log? I exponentiate. When I exponentiate, that will give me the expected count. Does that make sense? And that was why I said here, exponentiate to get rid of the logs. If they want to talk in terms of log, because somebody that is not in math say log expected, you're going to say, really? What do you mean? But if you say expected count, oh, okay, I got that. Okay, this way I'm going to stop. This is how Poisson regression work. But you know what? Tomorrow we're going to continue with another variant of logistic regression. Let me tell you, when we talk about variants of logistic regression, something that came out of logistic regression, but it's not logistic regression. It's like a logistic regression in another form. We talk about Poisson regression now. We're also going to talk about multinomial logistic regression. We're going to talk about ordinal logistic regression. Whether you talk about Poisson regression that we just done, talk about multinomial, or you talk about ordinal, or you talk about beta regression. They are all variants of logistic regression. But let me tell you what determine the type of regression to use is the nature of your response variable only. When your response variable is continuous, we normally specify linear regression. When your response variable is categorical, maybe two levels, categorical, two levels, we use binary logistic. If it is categorical, more than two levels, you know, we have more than two level race, more than two levels, right? Okay, we are not going to use binary logistic. We're going to use multinomial logistic regression. Multinomial. We're going to talk about that. Multinomial. If it is more than two and they are ordered, you know what I mean? Ordered, like I want to talk about customer satisfaction, where they're going to say very satisfied, satisfy, not satisfy, you know, stuff like that. Those are, you know, when you have it ordered, when you have classes of response variable ordered, then we use ordinal logistic regression. Does that make sense? But what if in a situation where the response variable is not categorical, it's not a continuous, it is not a count, but it's a rate? We know what I mean by rate? Maybe I'll talk about poverty rate, or I want to talk about infection rate, fascination rate. I want to talk about something in the region of 0 to 1. Then I'm going to use a beta regression model. We're going to do that in this class. You know, our models are not failing us, but are we using the right model? We don't just use a model. We need to, for us, understand the nature of the response variable. The nature of the response variable is going to be a driving force, pointing into the right model to use. Does that make sense to everyone? Okay, this way I'm going to stop. Make sure you all stay safe and have a lovely day. Bye for now, everyone.
Thank you. See you tomorrow.
You're welcome. Once again, no assignments this week, so that you're going to have opportunity to prepare for midterm 2. The midterm 2 practice questions have been uploaded. And you know what? I'm going to follow that pattern in the exam. Please study that. Where I want you to succeed. Make sure you all stay safe. Bye for now.